In this video, we're going to take our 3D scanned mesh and create a solid body version of that using Fusion 360. So stay tuned. Hey everyone, this is Matt with Learn Everything About Design. And in this video, we are going to take our 3D scan data from the last video of our KTM bar mount or triple clamp mount, and we're going to create a solid body version of that. So in this video, we need to tackle sort of a handful of questions. A lot of things come up when you're trying to do this work. The end of the last video, we talked about whether or not you actually had to scan. In this case, I've done a lot of hand measurements using calipers to get some of the precise measurements off the part. We're going to talk about that process a little bit, and we're going to go in and talk about things like the references that we're going to be getting off of the mesh data, how we can sort of position everything properly, and what information is really important and what's not. So in order to follow along, you can go to the description of the video and download the Fusion file that already has the mesh in it. I will note that this process typically involves inserting a mesh, and I'm going to do that on my end, but it's a little bit easier for me to just provide the Fusion file for you guys. So to get started, what we're going to be doing is navigating to mesh if you have your own scan data and selecting insert mesh. There are three different file types that we saved: an OBJ, a 3MF, and an STL. They're all going to be essentially the same in this case. I will note that they do have different sizes, and you can see the STL is quite a bit larger than the 3MF, for example. Now, there are pros and cons to using different types of files. So for example, the 3MF file can carry appearance data, settings from 3D printing, and an additive manufacturing slicer. None of that really applies to us exporting it from XScan. So I'm just going to stick with the OBJ file. Of course, you can decide which file type works best for you. Now, when we do this process, the first thing that we should note is the origin is based on where we aligned and set this up inside of XScan. So you can see that it's appears to be aligned properly. Again, we just sort of visually eyeballed where that point was going to be. And this is how it comes in. So I'm not going to do anything in terms of flipping the direction, the units or millimeters. We're just going to say okay. And now we have our mesh in place. Now, as I mentioned when we started this process, we have to think about things like the resolution, the quality of the scan. We ended up doing 16 scans of the top, 16 of the bottom. We can see kind of where XScan automatically stitched the two sets of point clouds together. There's a very clear indication on the difference between the mesh when it turned it into a mesh file. And that comes through in the data. Now, when we look at it on the screen, if we use Control and 4 to hide the edges, there's a visible line where we can see a little bit of jump or change that happened. And again, that's when this thing was scanned upside down, and it sort of cuts the plane off, and then it flips it, and we do it this way, and it cuts it off right here above that feature. Those are all things that we need to consider and think about, especially if we're trying to reverse engineer a mechanical part. Now, at the end of the day, making sure that you have precise measurements with a caliper or some other hand measuring tools is going to be a very important part of this process. You're not going to be able to rely strictly on this mesh data when you're trying to reverse engineer mechanical parts. You are going to have to measure. So with that in mind, let's talk about the first step of this process, and that is getting the coordinate system in the center of this hole. In order to do that, we're going to be using a mesh section sketch as a reference, and then we're going to be deleting it. Now, I've gotten probably this question more than almost any other question before, and that's how do you align a mesh in Fusion 360? Well, if you can avoid it, you don't. You simply want to do it in a true mesh editing software. That's going to be much easier. Now, as I mentioned, when we were in XScan, we don't have a way to put that point at the center of this hole. We just had to sort of pick a point on the mesh. We have a way around that in Fusion, and we want to make sure that we understand how this process is working. So the first thing that we're going to do is we're going to create a mesh section sketch. We're going to select the mesh body and select the selection plane, And then I'm going to move this down. And the reason I want to move this down is because I want the cleanest possible reference of that hole. That's where I want my coordinate system to be centered. The plane itself is at the correct height because we were able to select 3 points on this face. I'm happy with the location of the plane. I just want to move the origin. So we're going to create that mesh section sketch. Then in our sketches folder, we need to right click and edit. Now what ends up happening here is we need to use create and fit curves to mesh section. We want to make sure we select the fit curve type circle, and then we select the circle on the screen. What this is going to allow us to do is it's going to place a curve, in this case a circle, based on the deviation of our selected mesh. And this gives us a very important piece of this puzzle, and that's the center point of that hole. Now, it is important to note that this is not constrained, so make sure that you don't click on it, move it, resize it, or anything, because it has no constraints to the geometry. But now that we have this piece of the puzzle, we're going to go to our bodies folder and select the entire mesh, then use move copy. Now the piece of this that we want to make sure that we also are very clear about is that we're going to reset our pivot point to this position here, and we're going to say okay. Now what we can do from this point is we could use things like point to point or point to position. Now the tricky part of this is, remember, we created that mesh section sketch below. We moved it down 2 millimeters. So the height, the Z height, is not going to be correct. What we can do, however, is we can manually move it based on measurements. So what we're going to do first in this case is we're going to do point to point. We're going to go from our pivot point to the origin and show how the entire mesh moves. Now again, the problem with that is it's not at the correct height. The Z height has changed. The way that we can do this without affecting the location of our plane is to measure this, go from that reference point in the sketch to the origin, and toggle on our option to show our global coordinate system. What this is going to allow me to do is it's going to allow me to see that Z is 2 millimeters down, which is the number we don't care about. And then we have the X delta and the Y delta. Now the Y delta is 13.332 and the X delta is 0.147. Now, if you're doing this, if you're trying to follow along, the design that I provided already has this moved into place, but if you're doing this on your own meshes, make sure that you take note of those two numbers. You want to make sure that you write them down because you're going to use those to move the mesh over. Another important note here is that when we use mesh section sketches, and specifically when we're fitting curves to our mesh, that number is going to be an average or within a tolerance of that section of the mesh. So if we did this at 1 millimeter below the top instead of 2, those distances would be different. And they're probably 2 to 3 decimal places out, and we're talking about metric numbers here. So a very small difference, but it is something that we should potentially consider depending on what you're trying to reverse engineer. So now that we have those numbers, we can go back and we can use move copy. Once again, we're going to set our pivot point. And the main reason we're doing the pivot point is because we want to know exactly where we're starting. That was a point we measured. I can click on the direction, in this case Y, and I can say move 13.332. And then I can click on the direction that would be our X. And if we view this from the bottom, let's go ahead and move this. We want to move in the negative direction. So we're going to be minus 0.147. And what we should see is that will perfectly move the mesh into the center position of our origin. You'll also notice that the mesh section sketch didn't move with it, and that's because it was done before the move copy in the timeline. But it's okay because we actually don't need that mesh section sketch or the original sketch. We only needed it temporarily, so we had a starting point or a pivot point we could select for moving everything over. Now that our mesh is perfectly positioned, the other thing that we should really be careful with and think about is the orientation of our X and our Y and ultimately our Z are based on selections on the mesh in XScan. Now, I mentioned that we didn't do any processing. We didn't want to affect any of the raw data that we brought in. So that means that, for example, the overspray, or when I was spray painting in the cold, the areas where the spray paint dried just before it hit, those bumps could potentially affect the creation of a plane. We used the intersection of two planes to give us our X direction. We use selection of 3 points on a mesh to give us our Z normal. So all of these selections are important and critical to making sure that our geometry is aligned. What we're going to probably see downstream is that there's a slight misalignment in the part based on symmetry. But what we're going to be doing is using what we have here to give us essentially the best approximation of this part. Now that the part is in place and we're ready to start creating sketches and references, we're going to start by, once again, creating a mesh section sketch. Now, when I look at a part like this, I want to break it down into a couple of different pieces. The bottom piece appears to just be an extrude of this shape here. Now, the same thing with these little wings that come off the bottom. They're just an extension of that shape. So what I want to do is I want to create this shape first and extrude it up. Then from the top, I want to create this overall shape and extrude it down, and then we'll worry about the intersection between those two. But that's the general process when I'm looking at a part like this. So once again, we're going to select the mesh body, we're going to select the plane, and I want to make sure that I go down and get a clean mesh section. Now, whether that's 1 millimeter or 2 millimeter, that's really kind of up to you, but you want to find a place where you have a very clean reference. Now, the clean reference should also include the hole in the center. Now, because our part, the mesh in this case, is centered on the origin, and because I know from a measurement that the size of that hole is very specific, I don't necessarily need that center hole in this mesh section, but it is good to have as a reference. So once we're happy with the position, in this case I'm 4 millimeters up, we're going to say OK, and then we're going to edit that sketch. Now, every time we have a sketch that has a mesh section, and for my own personal purposes, I'm going to rotate this thing around. It's a bit easier for me to visualize that way. But anytime we have a mesh section, it will be expanded or a child of the sketch itself. So you can always expand that. I don't need to really see the mesh because we have this section here. But what I want to do is use some lines and just create a quadrant. Now, I'm going to be doing this in the upper right-hand quadrant, or quadrant 1, because this left section is pretty noisy. But what I want to do is I want to use these references. I'm going to use some mesh section sketches to fit curves to. So for example, in this case, I'm going to do a line, and I'm just going to create, as best I can, an average line here. I'm going to right-click and say OK. We're going to right-click and repeat this, and we're going to do it up here. And there's a very slight straight section on this part. We're going to right-click and say OK. And then we're going to do this again and repeat this, and we're going to make a line here, right-click and say OK. Now, each of these 3 lines, if we hide the mesh section, are going to represent the geometry that we're building. However, there is an important bit of this that we should understand. These are still averages of the mesh themselves. So the better job you did at prepping the part, the cleaner the mesh is coming in from the scan. And remember, I mentioned in XScan that we would do the post-processing of the mesh downstream. That's 100% true. Now, if I was trying to pick up curves off of this, say we're replicating a car fender, then I would 100% process the mesh. I would go ahead and remesh it and smooth it and make sure that all the references are clean, maintaining those edges and those corners. With a part like this, that I really need to go in with calipers and measure the mechanical dimensions, I don't really care as much about processing the mesh. I just want to select the sections of the mesh sketch that give me the best possible reference. I know that this part is symmetric, so I'm only working in the cleanest quadrant that I have, and I'm just going to simply mirror it around. So keeping that in mind, again, it's always going to come down to what you're doing with the data afterwards and how you approach it. So for example, if I were to fit a circle mesh curve to the center here, we can see that there are some bumps in that. And the circle in this case is going to approximate it. So you can see the max curve deviation is actually pretty small, but there are areas of that mesh that are below and above. Now those should be within that 0.04 plus or minus millimeters. That's the accuracy of the scanner that we're looking at. But again, that all comes back to how you prep the part. So what we're going to see is what I actually end up doing is with this circle, I will snap it to the origin, and then I'm going to give it a dimension. So in this case, I know that this is a 10 millimeter hole. When I actually measured it out, it was 10.007 or something like that. So I'm just going to use 10 millimeters as my reference. So this gives me a good approximation to make sure that I am close to what the mesh is, but I'm using the actual numbers that I measured. This also does help when we get into more cosmetic type features. But back to these references. So what I'm going to do with these references is I'm going to fix them. And when I fix them, what this is going to allow me to do is I can extend these out, for example. I can extend this out and I can snap that to the line here. But the problem with just extending these out is these aren't necessarily horizontal or vertical. So when I go to mirror this geometry over to the other quadrants, it's not necessarily going to give me a smooth reference. So generally what I would do is I would turn these into construction, and I would use their intersection points for creating actual geometry. So snap here, I'm going to draw a horizontal line. I'm going to snap to that intersection, and I'm going to draw a line down to here, and then maybe snap to this intersection and draw a vertical line. So when I drew a vertical line, you can see that there is a slight variation here, which again, the verticals and the horizontals, those are extremely important when we come to mirroring things across. The angle of this edge, not really as critical, so snapping to the reference geometry is perfectly fine. But I do want to trim these and make sure that they do end at that sharp corner. So now that I have this, these vertical and horizontal lines, I'm going to use X to convert them to construction. You can also do it by selecting your line and toggling that in the sketch palette, but X is quite a bit quicker. But now we want to mirror this. Now, when we do this, you'll notice that it's trying to select the object underneath it. So what you have to do is just move the cursor around until you're getting the correct line. If you have trouble, you can always hold down the left mouse button, and this will bring up a menu of the lines, and this will be a little bit easier to see. Then we're going to mirror across the vertical. We're going to repeat that process. So once again, making sure that we select the correct lines. If you have trouble, hold down the left mouse button, and usually that makes it a little bit easier. We won't have that problem on the bottom unless you happen to select where one of those reference lines is. And then now we'll just mirror across the vertical. So this will give us a complete closed profile that we can use to extrude that bottom shape. And then I'm going to add the fillets after the fact. So now that we have this reference, I'm going to finish the sketch. Generally, I don't keep the origin on when I'm modeling. I generally will turn that off. But in this case, I'm going to leave it on for this first part. We're going to go to solids and hit extrude, or you can hit E on the keyboard. And the reason we're going to sort of turn the origin back on is because we want to extrude from an object, which is that original plane. That's the basis for our entire part. And I just want to make sure that I come up far enough that I am past the intersection or the transition between these two solid bodies. We're going to say OK. Now I can hide the origin, and I'm actually going to hide the mesh just to take a look at what we have. Control and 6 will bring back my edges if they're off. And overall, I mean, that looks like the part. It seems pretty reasonable. At this stage, what I generally will do is hit A on the keyboard or right click and change the appearance of the body. Give it a color that's a little bit easier to see. This will help us see the differences between the mesh and the solid body. So as we move this around, what we want to see is the mesh just barely peeking out through there. Over here, that looks pretty good. You can see it's a little bit darker there. And this is likely because the part was slightly rotated, or the accuracy of the scan in that position is a little bit off. You can see here, it looks pretty good there. As we rotate it around, there's a little bit of yellow peeking through. Same thing over here. This is the area where we had a bunch of bumps from the spray paint. So I know that one is not going to work very well. But overall, that looks pretty good, and we can verify this by measuring the physical part. So this side and this side over here is flat, and there are flats here, so we can get calipers and we can measure it. But at this stage, I'm going to use F to fillet, and I want to add a fillet to these corners, and I'm looking for sort of the same thing. I want to see when the yellow just kind of disappears. And that happens at 3 millimeters. I can just start to see the mesh underneath. So because that's something that's really hard for us to measure, using this method of doing the fillets after the fact can help. You can also just get them from a mesh section sketch as well, but that's a little bit trickier because you are then, again, dealing with the highs and lows of the mesh. So for me, this works pretty well. Now I'm going to repeat the fillet. This time I need to do these edges here, rotate it around. And then we need to figure out when those just start to disappear. I know that it's not going to be 3 millimeters. We're going to use this side. This side seems to be a pretty good reference. I'm going to say 8 millimeters. That looks pretty good. If we go up to 9, that looks even better. 10 is probably a bit much. So it looks to be about 9 millimeters on those corners. It gives me a consistent yellow and gray finish as I rotate this around. Now the reason I'm rotating it around, because as you zoom in and zoom out, you actually notice that as you zoom out, more of the mesh peeks through, and as you zoom in, more of the solid peeks through. So it's important that we do rotate things around a little bit. I know it's probably disorienting to watch. It's kind of part of the process. So now that we have the hole in the center, we've got the basis for the design, we're going to add these little pieces on the top. Now, this is an area where measuring the distance between these is critical. When we were doing this in XScan, we did make planes for the top and bottom. Those planes obviously didn't come through. We could have measured the distance between those inside of XScan. I also just measured the physical part because you can see there are little like spikes here. So for this part, I'm going to go and create a sketch on this face. We could use a mesh section sketch. However, I know the distance between those two edges, again, because I measured them. So what I'm going to do is I'm going to create a horizontal line. Actually, you know what? Let's do this a different way. Instead of creating a horizontal line, I'm going to do a center point rectangle because everything is centered about the origin. And the length of this doesn't really matter to me, so I'm just going to make it 60 millimeters. But the width between those two flats, that's important. So it's actually 20 millimeters. It's actually 20.066. So because I'm not going to be machining this part, I'm not going to get down to that level. But remember that these parts were anodized, and the part specifically that I scanned was painted on top. So that 0.066 is likely based on the coatings. So I'm not going to factor that in. I'm just going to use nice clean numbers here. So now that we have this, what this ends up giving us is these little sections over here that we can extrude. So E on the keyboard to extrude those up. And from measurements, I know that that's 1.87 millimeters tall. And then we want to take a look at our mesh. So you can see that it looks like it's a little bit above, but these are actually rounded corners. Now, one trick that you can do to verify this is you can take the body, right click, and go to opacity control and set it to somewhere between 20 to 50%. And then you can kind of look through the side of the part. And what you want to do is you want to see where you're actually getting those high and those low spots. Now you can see that a couple of the high spots are hitting and the low spots are fairly low over here, but actually tend to average out over here. If we look at it from the other side, again, sorry about the disorienting view. We'll look at it from the side here. Once again, you can kind of see the spikes are going above and the lows are below. I would go off of the physical measurement of this rather than the mesh in this case, especially the differences here. It's likely going to be somewhere between 1.7 and 1.8 millimeters. Just again, something that you have to really look at the measurements that you have. But now that we know that, I'm going to go back to the opacity, set it back to 100, and then fillet these corners. So F on the keyboard, I want to add fillets to these corners. And as we begin to pull that in, we want to figure out where they start to cross. And 0.5 looks okay. I think I'm okay with that. And then I'm going to do F on the keyboard and do a 0.5 fillet over here. And you'll notice that that leaves that little spike. That's the mesh underneath. There are highs and lows, but that looks pretty good. And control, we can add additional edges. We can fillet those. If there's a fillet on these inside corners, you can add it. For this part, I don't believe that there is because it fits pretty tightly to another piece. But there are uh, fillets and deburrs on those holes. So that looks pretty good. I'm going to say okay. And once again, basically we're just building that bottom feature and working our way up to build the rest of this. So I'm not going to worry about the counterbore yet because that affects both pieces. So what I want to do at this stage is I want to make a plane for the top of this that I can use as a reference for extruding the mesh section sketch. So for that, again, I physically measured the part. So what I'm going to do is create an offset plane from here. And that offset plane is going to be a negative value in this case because it's based on the normal of that face. Now for this part, it looks like it's about 39. It's 38.8366 is what I measured. Again, this is calipers on a desk. So 39 is probably close enough, honestly, for this part, but I'm just going off of those measurements. So now this plane is a good reference for us for both a mesh section sketch, but also the final features. So what we're going to do is go back to mesh, create another mesh section sketch of this body. The plane we're going to use is this, but again, we're going to pull it down to sort of grab those references. Now, the way that this works is a little bit tricky because, again, we had some areas of the design that sort of started to disappear. But in theory, when we look at this from the top, this geometry should just be extruded straight down. This is going to be much easier to machine. These parts are all CNC machined. They're not going to have any crazy tapers on them. So I should be able to pick that up from wherever I want. But the tricky part about this is that as we get down to where the full body of this is right here, we start to lose the rest of that. So you have to kind of pick and decide which geometry you want, which is going to be the better option. I'm going to go down about 3 millimeters and say, okay, hide the solid body, and then I'm going to edit this sketch. I'm going to hide the construction plane for now, but edit this sketch. Once again, I like to view it sideways, so I'm going to rotate it around. But what we're going to see here is that the origin of this plane is kind of off. So I'm going to bring back my default origin and use project because I want to bring that center point into my sketch that I can use as a reference. So now I have a reference for the origin, or I could have grabbed the center of that sketch that was used to create that hole. Either is fine. So the next step for me is a little bit tricky because it's going to be based on some measurements, some visual references, because we don't have that geometry right there. I know from measuring it that it's actually essentially just a large circle. So what I want to do is use horizontal to make sure the center of that circle is horizontal here. I know that this part is symmetric. And then I need to use my hand measurements to determine the diameter of that. Now, one thing we're going to notice is that it fits pretty well over here. And down here, it's a little bit off. And again, this is partially based on the alignment of the scan in XScan. We had to pick planes based off mesh. So even plus or minus 0.04 can set your design off just a little bit. So at this stage, especially with mechanical parts, we have to think more about the design intent of the part rather than the actual geometry. So I'm going to use D on the keyboard, and I'm going to give this a 32 millimeter dimension. And once visually it looks like it's in the right spot, I'm going to give it a distance from the center here. And 3 millimeters is not quite right. You can see it's sort of offset here. If I go to 3.5 millimeters, that looks quite a bit better. We can also see that it's essentially in the same position relative to these two holes. And for those two holes, what I'm going to do is create some circles. Again, C on the keyboard is the circle tool, which you can use. I'm going to just create one here and one over here. Make sure that all of these are horizontal with the origin. I'm going to make them equal, the same size. And I know they're distance apart, again, from measuring. So I know that these two holes are 38 millimeters apart. And then what I want to do is I'm going to hit escape to get off my dimension tool. And I want to position those so they're at the correct position in the holes. Now it can be a little bit tricky to do. We do have some mesh data here. So we could go into create fit mesh curves and try to fit a circle to that reference. However, if you only have partial references for stuff like this, so for example here, that circle is obviously not a good reference. So in some cases, you might just have to measure and get as close as you possibly can, knowing that we actually scanned threads. So for me, what I ended up doing is making this a little bit bigger until it approximately aligned with the outside, and then using my dimensions from the origin to here, looks like about 15.5 millimeters. So the size of this, I'm going to make this 17 millimeters. Both of those are going to be the same. And again, we have to look at an approximation of what we think this part should be. We know that the designers originally wouldn't have made the distance between these 38.6175 or the diameter of the outside of this part. It's all going to be, or I should say all, generally it's going to be nice round numbers for a lot of these dimensions. So when you're looking at the difference between a mesh and you're looking at the different, well, a scanned mesh and the difference between picking a dimension that makes sense, I would always err on the side of the dimensions being round. Of course, if we know that this part is metric or standard, that's going to make a big difference. Metric numbers, I've found, generally tend to be nice round numbers. So what I'm going to do at this stage is I need to build out the rest of this. And the way that I'm going to do this is I'm going to make use of symmetry again. So I'm going to come over here and just draw a straight line, and then I'm going to make that coincident with the origin. So what this allows me to do is it allows me to place that line at the origin, which gives me just a half section to worry about. The next thing I need to do is I need to connect these all together. Now, as I mentioned, design intent is important, and what we want to do here is we want to make sure we notice that this one on the right-hand side looks like it fits pretty well. The one on the left-hand side fits better down here than it does here, which leads me to believe that we're maybe half a degree off the rotation of the overall part. So once again, we're going to just have to make a decision as to what we want to do. So what I'm going to do is fit curves. I'm going to do straight line. And I'm going to create a straight line here. I'm going to come over here and create another straight line. Right click and say OK, and then hit escape. I'm going to delete this line here because I don't actually need it. We'll just select it and delete it. And then if we hide our mesh section, what we're left with is some references. So these references are going to once again be construction, and I also want to fix them. Remember, when we fix them in space, we're only fixing their angle. We can still actually extend them out quite a bit if we need to. But what this allows me to do is it allows me to create lines that go from here to here and from here to here. And what I want to do is make sure that these new reference lines are tangent with the surrounding circles. And I want to sort of verify those positions relative to my references. Now, what I've found is if I have to make adjustments, you can see that these look to be a little bit on the inside. If I have to make adjustments, I can go back and just sort of do that. But you can also add dimensions. You can see that we're 179.8, so 0.2 degrees off of being parallel. That's pretty darn close. We can also measure the point to the edge, and we can see that we're 0.049. And again, that's plus or minus 0.04 millimeters was what we were expecting the accuracy to be. So that's kind of well within the range of what we would expect to see the difference between a measured physical part and potentially the scan data, which is why it's important that we don't just create that line and make it hit this circle. We want to make sure that we have tangency between our reference lines and the surrounding geometry. So overall, this looks pretty good. So we're going to finish. I'm going to hit E to extrude. And notice that I didn't include those holes. That's something that I'll go back and do later. But for right now, we do have those center point references that we can use downstream if we need to. So remember that this was sort of down below the top of our part. So this is where we're going to bring our plane back, and we're going to start from the plane as our object. And we just need to make sure that we go down far enough that we're below our reference edge, because we're going to end up splitting this up into multiple solid bodies. So this is going to be a new body. We're going to say OK, and just take a look at it from the side. Now, at this point, we're 35 minutes in, and I haven't saved this thing once, so it's a great idea for us to go ahead and save this. So I'm just going to call this bar mount video, just so I remember I did it during the video. But once again, we also want to change the appearance of this to make it clear. I'm going to give it a red appearance, and this will help us just sort of identify the difference between it. Now remember, this is also just half of our part, so it's a good idea for us to mirror this over. I'm going to mirror this about its center line, which should also be the plane, and we'll join them together. And we can kind of see that, again, that marbleization of the mesh through the part. So we know that we're pretty close to being on track. There's a little bit more mesh on this side and a little bit less on this side. But once again, we're looking at that plus or minus 0.04 millimeters, and we measured that difference specifically in our part here. So the next part of this process, or the next couple steps, would be to cut out the bar opening, and it would be to cut the bottom of this out. And the way that we're going to do this is we're going to cut the bottom off first so we can see how to do that. And I'm going to do that with just a side sketch. At this point, I could use a mesh section, but remember that there are holes in here, and we scan those threads. We're probably not going to get the greatest reference. So I'm going to do this visually because this part of the clamp is less critical than other areas. So what I'm going to do is just visually look for this line here. We could transition this to an arc, but this is kind of an interesting curve. So I'm probably going to do that with a spline. I'm going to say okay there. I'm going to come over here and again, just kind of draw that line. It looks like we've got a horizontal transition here. So I likely do this in two separate sketches. I'm going to just move this around until it visually looks like it matches that line there and this line here. Maybe extend this one out a little bit just to get it out past the part. Now, generally, I work with fully defined sketches. There are times when it makes more sense to define a sketch than others. And in this case, it's just going to add a lot of time to fully define these. I do suggest that you come up with some dimensions for your parts, even if we don't do it in this video. So now that we have that sketch, we're going to use split body. We're going to split this body here with this sketch. We're going to say okay, and then right click and remove that other piece. Now, removing it's a critical part. We can't delete it because we want to make sure we keep all the previous references. Now, we have to address the fact that we need to cut out this section as well. Now, it's actually quite a bit easier than it looks. And what we're going to do is hide the body once more, create another sketch on the side. And this time I'm just going to use a spline. And the main reason I want to use a spline here is just simply to show that it doesn't have to be perfect necessarily, but what we want to do is we want to come out below our part, move these points around if we need to. This is probably going to be pretty hard to see on screen, so what I'm going to do is change the opacity of the mesh, Control and 4, which is going to essentially hide all the edges, which makes it a little bit trickier to see. But again, all we really are trying to do is take this curve and match what we have on the mesh. So again, if that's hard to see, sometimes you can also turn on curvature combs. Might be a little bit better visual reference there. But overall, let's go ahead and bring the opacity back up. That looks pretty good. It's pretty close. And again, it doesn't have to be perfect. So once we're happy with that, we're going to finish the sketch, bring back the solid body. Once again, use split body and get rid of that extra little piece. So find that little piece, right click, and remove it. Now at this stage, we've got this yellow body here, and we've got the red body that we need to combine together, and then we can deal with cutting away the holes. So there is a hole in the bottom of this part. Again, I'm not too concerned with making it go all the way through, but I need to add a couple fillets. So F on the keyboard, I'm going to add fillets here before I combine these. We can bring the mesh back and try to visually get it to match the underside of this. I think 8 millimeters looks pretty good. So I'm going to say enter, and then we'll use combine and we'll join these two together. So we want to make sure that when we join these together, we then start to think about blending them. And once again, we're going to do that with a fillet. and start to drag this out. And I'm going to bring back the mesh, and I want to find the value where it just starts to come through. So you can see here, we're just starting to see the part come through the mesh. So it looks like about 7.5, maybe 8 millimeters is about the sweet spot for that. So you can rotate it around. You can kind of see we're seeing some mesh through here. This is all red here, probably just because the angle of that edge is a little bit off. But overall, I think that looks pretty close. 8 millimeters makes sense. Again, if you think about CNC machining and the size of the tools that would be used, that looks overall, that looks like it would probably be pretty close. Then F one more time, fillet, we'll do 0.5, which is the same size we used on the bottom, just to kind of deburr that edge. And we'll worry about the top next. So far, everything looks pretty good. I think I want to take care of cutting out the opening for the bar next. And to do that, we are going to do, once again, a mesh section sketch. This is the mesh body. The section is going to be just the side plane. And this one's a little bit trickier for us because we're getting all kinds of crazy references, right? We've got the center hole through the bottom. We've got some of this bar mount, but there's a counter bore here. And if we try to fit a mesh curve here, it's not going to give us the reference that we think. So if we do this and say, try to fit a circle to this, it is going to include a portion of this where we've got these threads and a portion of this down here. So that doesn't give us a very good reference, and this one over here doesn't either. So the way that I approach this is I'm going to do an arc here. I'm going to repeat the process and do an arc over here. And remember that these are underdefined. So what I'm going to do is fix the endpoints, hit escape, and I'm also going to turn these into construction with X on the keyboard. Now the reason that I'm doing that is because I know the size of the bar. I know where the bar is going to be positioned. I know the size of the diameter of it, but we can use a couple of points, a couple of coincident points to the circle to define this. Now, if I add a third point, that'll fully define the circle, but I also want to drive the diameter of this. Now, when we're thinking about a handlebar, in this case, it uses 1 1/8 inch handlebars. That ends up being 28.575 millimeters. So when we do that, notice how it shifted it down. So what this tells me is that the coincident relationship that I applied over here is likely not going to be where we want that to be. I probably want to make these 2 points coincident. What that does is it ends up pushing it up. Looks pretty good over here. You can see it starts to pull away there. But overall, that gives us a better fit, a better alignment. And this is why I avoid 3 points of contact to define that circle, and I want to drive it based off the diameter and just 2 points of contact, because that will give me a better fit overall. Now I can finish the sketch. I can go back to the solid body. I can use E to extrude. And I'm going to push it through all. I'm going to do 2 sides, and so lets me do through all on both sides. We could also just do symmetric, and that would be the same because we did mirror the part. So now it looks like we've cut through. The last step of this process, or the last couple steps, is to do the threaded holes on the top, to do the counter bore, and then we also have to just deburr things. So the counter bore is something that I know its height based off the bottom of the part. You also see there's this extra little piece in here for this hole. That's simply because of the difference in height between this part. It's actually part of that wall coming down. We'll deal with that in a second. But with the counter bore, we could define it using the hole feature. However, that means that we would need to select it from the top, which is a bit tricky. And we know the references based on how it was measured from the bottom. So what I'm going to do is I'm actually going to create a sketch off this bottom pad here. I know that it's based off the center, so C on the keyboard. I know the diameter of the counter bore is 18 millimeters. And then I can E and extrude that. And in this case, I know that I can offset it. It's going to be a negative value because of the direction of the arrow on the screen. It's going to be negative 17.375. That's how far it is from the bottom of the part as if it's sitting on a table. And then I can just pull that all the way up through. So that gives me the counter bore at the right location. However, you can see there's still that weird little step there. I can use direct modeling to try to select and delete it. And if that doesn't work, then we can always just extrude the hole all the way through, but that gives us the result we need. So now we need to determine where those two tapped or threaded holes are going to be. Remember, we do have a mesh section sketch that gives us those reference locations. So if you want to use the option to create holes using points, we can always use P on the keyboard and project those center points up. Now, I'm a big fan of doing that over defining them in another way, simply because we're using geometry that was defining earlier on in the process. And if we project and we link to that, if we make changes earlier in the design, then it'll update easily. However, if we did just a single hole on here, we could position that based off of this selected reference. So we could select that arc, knowing that the center point is centered on that arc because of how we defined the part. That would also be perfectly valid. But in this case, we can use the from multiple and just simply select our sketch points. I want to make sure that it comes down through the part on that one side. The way that it actually works on the physical part, and I'll put an image of this up on the screen, is it didn't go all the way through on this side. So it just kind of cut partially through. Now, these holes are 8 millimeters, and we have the option to turn on modeled, which will cut physical threads through it. If we turn that off, it'll just do an appearance, and the hole size will be the minor diameter of the hole, so basically the drill size. And that's something that's important because there will be a difference in the overlap between this edge and the holes. On the physical part, that actually does sort of bleed over, and there's a chamfer on that edge. So that's something to keep in mind. When you do modeled, it'll actually physically cut the threads. And if you turn that off, it's going to give you that minor diameter. For this part, I'm not going to cut the threads. I'm just going to leave it as the appearance. We're going to say OK. And then I want to go back and just add a couple fillets. Now, if I add a fillet all the way around here, let's just grab all the edges, and we make it 0.5. That's essentially what we have on the part. There is a deburr here, so I'm going to hold down Control. There was a chamfer on these upper edges, so I'm not going to use a fillet there. We could deburr that as well if we wanted to. On the physical part, it probably has a chamfered edge and not a filleted edge. But overall, I mean, that's pretty darn close to what the actual part looks like. So I'm going to use a chamfer. The chamfer wasn't a countersink per se. It wasn't looking at countersinking a screw. It was just cutting out that edge for, making sure that it wasn't a sharp edge on the thread and making it a little bit easier to thread. So we're going to say OK, and that is our part. That's essentially the end of it. Now, what do you do from here when you've designed a part like this? Well, again, we'll just do a quick recap. We need to think about whether or not we need to scan the part at all. Now, the reason that this part was a good candidate is because there's geometry on it, such as the side cut here, that would be really difficult for us to measure. Those were done just sort of freehand with sketches and a spline. That geometry, not really being critical to this design, not a big deal if we just sort of made it up. But that's the main reason why this part would get scanned. Other things on the design are easy enough to measure: the overall height, the hole sizes, the locations, the width of it, all that information, knowing the bar size, being able to measure where the counterbore is. All of that stuff is things that we had to measure anyways, whether or not we scanned the part. So whether or not I scanned this part, again, it just comes down to how accurately you want to try to replicate some more cosmetic details. Now, I think we did a pretty good job replicating that. Control and 4 to hide the edges. I think this looks like the physical part. I think this looks pretty darn close to the physical part. If you rotate it around to the different views, if we bring the mesh back, I'm going to go ahead and just move this off to the side so we can see. I mean, I think that's pretty darn close to the original part. I think we've got all the details. Looks like there may have been a little bit more of a fillet there than we have here. It could just be because that's scanning into a corner. We might not have great detail there, but everything looks pretty good from the top. And again, these do have a chamfer on them. They actually have the threads. whereas we just have the threaded appearance, which gives us the minor diameter. So there is a difference visually between how far those threads bleed into where the bar mount is. But again, that's just kind of part of the fact that we're looking at a true hole here and not the physical cut threads. So you could certainly physically cut the threads through and get it to be a little bit more accurate. So for example, this one here, when we look at the threads cut right there, you can kind of see the threads cut on the scan if I do Control and 4. So very, very similar in nature to the way in which the holes appear when we physically cut the threads through. But again, it's not needed, especially if you're taking this thing to manufacture, if you're going to CNC it. Having this clean hole is a much easier solution, knowing what the tap size is going to be. So at the end of the day, my conclusion from the last video is going to be the same as the conclusion from this video. Scanners work really well for a handful of things. So if you're replicating cosmetic parts like car fenders and hoods and pieces that are much more difficult for us to measure, scanners really are very good there. They help us capture that data and we can use it for manufacturing, whether it's recreating a part, whether it's inspecting the accuracy of the manufacture process. So for example, if you are stamping fenders and you have the original CAD data, you can scan the manufactured parts, compare the scan to the CAD data, and get an idea if the manufacturing process is okay, if there needs to be some adjustments or tweaks. Same thing for things like injection molding or even 3D printing. If you have the CAD data and you produce a physical part and you want to see how close the physical part is to the CAD data, you can scan it, and it's really good at being able to do that. Again, with this sort of disclaimer that you really have to think about the prep of your part, the accuracy of the part, any possible coatings on the part. These pieces were anodized. The one we scanned was also spray painted. So there is an appreciable amount of buildup that happens on parts that we need to account for. The kinds of parts that I would not scan just to have would be purely mechanical parts that can be easily measured. This part could have been relatively easily measured. The triple clamp, those parts can be easily measured. The brake lever is kind of one of those in-betweens where the data is valuable from the scan process, even if it's not required to reverse engineer the part. But overall, I think that hopefully gives you a good idea of the approach to the process of reverse engineering a part, thinking about the accuracy of the scan data, thinking about the design intent, things like symmetry, nice round, clean dimensions. This part was metric. I know it's metric simply just based on the manufacturer. But knowing that, again, if the part was designed in inches or millimeters, that will help you sort of pick and nudge those dimensions into the right realm. Now, there is one last sort of piece of this puzzle, and I do plan to cover it in another video, but it'll be a different series. And I mentioned it at the end of the last video, and that's using the scan data to design new parts that fit around the scanned data. So that's an instance where scanning makes perfect sense, especially if you don't have the original CAD data, you don't have access to it, you don't have a great way to measure something. That is a situation where using scan data can be very valuable because you just don't have access to the original. So with that out of the way, if you have any questions on the process or you got hung up anywhere along the way, please let me know, leave a comment. And if you have any questions in general, then also reach out. So as always, thanks for watching, and we'll see you in the next one.